Hi friends, today I'm going to start lecture 24 on our helicopter dynamics series and we will discuss the Galerkin method. I am Dr. Ranjan Ganguly. Now we have seen that it's not possible to find the natural frequencies of a rotating beam using classical methods or get a closed form solution as we can do for non-rotating beams. Therefore, people turn to some different methods to obtain these frequencies. And these are typically classified as approximate methods. The most important of these being the Galerkin method and Rayleigh-Ritz method, which we are going to discuss in the next two lectures. So today's lecture we are going to focus on the Galerkin method, which is based on the differential equation. So Galerkin method is based on the differential equation governing the system. And what we do in the Galerkin method is that we have to presume some deflection, which is a function which satisfies all the boundary conditions. And this particular function plays an important role in the Galerkin method. It becomes a basis function. Now the next thing we do is we substitute this assumed deflection into the differential equation. Now in general, this deflection is not going to be an exact solution of the differential equation because in most cases we do not know the exact solution. In those cases, you are going to not satisfy the differential equation to 0, you are going to obtain some small number. So we say an error is obtained. Now essentially we minimize this small number by integrating it over the complete domain, and before we integrate this function we weigh it with the basis function. So that is the basic idea behind the Galerkin method. So next we are going to explain this mathematically. So let's start with our governing differential equation for the rotating beam. So we have the flexural term, we have the centrifugal stiffening term, the inertia term, and we have the forcing. Now we presume a solution, so we call it W subscript app, and this solution is typically expressed as a series I is 1 to capital N YIR QIT. So essentially we assume the solution to have a spatial part and a time dependent part, and we assume n series for this particular function. Now one of the requirements in Galerkin method is that this assumed deflection shape YIR must satisfy all the boundary conditions, and this is a particular requirement in the Galerkin method, and it is sometimes difficult to meet because while it's easy to satisfy the geometric boundary conditions, which are the boundary conditions typically governed by geometry such as at the root of a cantilever beam, deflection and slope should be 0, it is more difficult to satisfy the force boundary conditions. For example, for a cantilever beam, the moment and shear force at the tip of the beam should be 0. But you can of course find such functions for cantilever beam. We'll discuss that later. Now, if you were lucky and you somehow figured out this solution as the exact solution of the differential equation, this PD would be satisfied and you would get an exact solution. Also, this n value here, that is the number of terms of the series which you keep, is selected by the user. Now typically in these approximate methods you can use 1 term, 2 term, 3 term, 4 term, and so on. And as you increase the number of terms in the series, the method essentially converges. That is, the frequencies become more and more similar, and finally they become same to a certain number of decimal places. So these methods are typically used to obtain numerical solutions. So now we take this differential equation, and what we are going to do is we're going to substitute that W is W app. Now when we substitute the approximation, we get this here. Now this function is not 0, so this function is nothing but this left hand side minus fz. Okay, so this function is not going to be 0, it is going to be some value, and this value is going to be dependent on r and t, because this entire function is dependent on r and t and is having different values at different points in the domain. So now this is the function here, and what we do next is we substitute this series solution into this equation, and if we do that we get this equation here. Now what's happened is that wherever we had derivatives with respect to time, the qi got differentiated, and wherever we had this derivatives with respect to r, the yi term got differentiated. So we denote the differentiation of the yi terms with dash, where keep in mind the dash is d by dr. So this is what we obtain, and now we have a series here I is 1 to n. Now essentially we want to drive this epsilon function to 0. And if you look at this equation, what we can play around with are the qi's, because we already selected the yi, so the basis function has been selected. So what we want to do is we want to find qi such that the epsilon term is driven to 0. So one of the ways to do this is to essentially say that this epsilon multiplied by the basis function, which is also the weighting function in the Galerkin method, and integrated over the entire domain, which in this case is 0 to r, is set equal to 0. And now if we multiply this epsilon by yj, we are going to obtain j such equations. So j is 1, 2, all the way to n. Now by doing this, we are able to write this in a summation form. And you can see here that all the terms which were in epsilon and before that in the differential equation are here, and they have been essentially multiplied by yj. So you will see yj here, yj here, yj here, and yj here, and of course the drs have come throughout. Now one of the things which happens now is that you have terms which involve q double dot, and then the remaining terms involve q, and of course there is a forcing term which is not dependent on q or q double dot, and that goes to the right hand side. So this equation can be written in terms of a mass matrix and a stiffness matrix and a force vector by collecting the different terms which are there as coefficients of qi double dot, qi, and then on the right hand side. So this is the expression for the mass matrix. This is the expression for the stiffness matrix. So the interesting thing in the stiffness matrix is that you have an additional term due to the centrifugal force or the tension. Now if you had T0, then you would only have these two terms, and that would reflect a non-rotating beam. And the Qi term on the right hand side, or coming from the right hand side, is dependent on the forcing. So we can write this in matrix form because it looks nicer, it's more compact, and we are often more familiar with matrix notation. So essentially what has happened is that the partial differential equation has been reduced to this matrix equation of size n by n. So the fact that we took the series solution has essentially truncated the degrees of freedom of the system. Now there are qi is 1 to n degrees of freedom for this system. Now this is typically a coupled set of differential equations, and today we are going to be only interested in free vibration, so we are going to set q equal to 0, because remember, free vibration means no forcing. So what have we done? We started with the PDE, we presumed a solution I is 1 to n, basis function into qi, and now we are going to also assume simple harmonic motion. So we assume qt can be written in this form, and then essentially the matrix differential equation becomes a simple eigenvalue problem. or what is more commonly known as a general eigenvalue problem. So most solvers will give you a solution of this problem. If you use MATLAB or some other solver, if you feed that solver the M and K matrices, you are going to get the solution of the natural frequencies and the mode shapes. Now, for many blade vibration problems, it is convenient to express displacement in terms of beam functions. So for example, we could take W app and we could express it as a series of the mode shapes phi r and qit. And this is where you see the mode shapes are important, because you can use the mode shapes of the non-rotating beam here, because you know the non-rotating beam mode shape satisfies the boundary condition. So if you have a non-uniform beam, or you have a non-uniform rotating beam, or a uniform rotating beam, you can always use the basis functions or the mode shapes coming out of the uniform non-rotating beam, which we have derived before. So that is why beam functions are very important. Now, one of the advantages of using beam functions is that we saw that the beam functions have certain nice properties. They are orthogonal, and because of this the matrices are going to be relatively simple in nature. Also, beam functions by their very definition satisfy all the boundary conditions of the problem. So if you are dealing with the cantilever beam, you pick the beam function corresponding to cantilever beam. If it's a simply supported and free beam, then you can use the beam function corresponding to those beams, and so on. Now these are typically specified in different vibration books and also in handbooks of structural dynamics. Now we saw that the procedure for the Galerkin method is relatively simple. One of the difficulties is in choosing the basis function which satisfies all the boundary conditions, and many people have come up with these basis functions which you can use. Also, sometime integrations which you need to do to calculate the mass and the stiffness matrix can become quite difficult to do when you are using the beam functions. Now, one of the things the Galerkin method would do is that it would estimate the solution to be slightly more than the actual solution, which would be the exact solution of the problem. So the calculated natural frequencies are typically more than the correct value. So this is one of the things you can use to check if somebody has implemented the Galerkin method properly, that you essentially will become closer and closer to the exact solution as you increase the number of terms. If you use a simple one-term solution, you will have a much higher prediction. And also, the divergence you get from the exact solution increases for the higher modes. And a large number of terms are needed to get a good estimate for the higher modes. So finally, before we end, I will give you a simple example for a uniform beam and use a one-term solution. So if we use a one-term solution, we essentially write W app as a basis function into Q. And here I have used this basis function. And you can check out this basis function should satisfy the geometric as well as the force boundary condition. That is, y1 at 0 is 0, which you can see straight away. Y1 dash at 0 is 0. Y1 double dash at R should be 0, and y1 triple dash at r should be 0. Now once you have done that, you can obtain m11 as this integral, which comes to the value 26 by 45 mr, and you can calculate k11 using this integral here, and you get a value for this. You can divide these two to get the first natural frequency prediction, and that comes to this value here. Now here you can clearly see that if rotation speed is 0, then you get an expression similar to what we obtained for the exact solution for the non-rotating beam. So it is EI by MR4. So dimensionally we are completely fine. And you have here 12.46 EI and 1.173 into rotation speed square. So this is how you can obtain good solutions, closed form solutions, which you can use to calculate the rotating frequencies using the Galerkin method. Now, if you use more terms here, then your solutions will get better. So, in the next lecture, I'm going to discuss the effect of gravity on the flapping equation, and then in the further lecture, we are going to discuss the Rayleigh-Ritz method, which is a competitor to the Galerkin method. See you then.